Günter Ludwig was born in Zackerick in 1918 and is now professor of the foundations of physics at Philipps University of Marburg in Germany. During the Second World War, he was a member of von Braun's team and later was in contact with Werner Heisenberg, author of the famous uncertainty principle, which is a subject not unconnected with what we'll be talking about in the course of this meeting. Professor Ludwig's central work, Foundations of Quantum Mechanics, may possibly be the most profound, extensive and committed reflection on the philosophical problems arising from one of the most significant revolutions in the physics of our times. He is here because his ideas, as well as being sound and clear, are not precisely the most typical in this discipline.
Thank you very much for this kind invitation to this beautiful occasion here. It makes it possible for me to give some, as I hope, provocating remarks to some problems. Galilei has indeed founded the method of physics. He has based physics on experiments and mathematics. He believed that mathematics is appropriate to describe nature which is revealed by experiments. He rejected philosophy as a method of physics, which prescribes how physics ought to look like. Unfortunately, the successors did not always pay attention to the methods founded by Galilei. We shall see this later. Correctly understood, Galilei has introduced physics as a further development of craft. We shall see that physics is indeed a craft, a very complicated craft that can be handled today only by myriads of the best qualified physicists. During the historical development, and also today, there is a danger to pursue wrong ways. One of these wrong directions was the so-called determinism. Geometry was perhaps developed first by craftsmen who wanted to measure distances and areas. The development to a pure mathematics should not be condemned, but then on philosophical grounds one looked down on the application of mathematics by craftsmen as a pollution of the pure mind by matter. This contempt for craftsmen and their work can become one of the causes to lose the way of physics. And today we find again persons who condemn physics and technology. It surely was no accident that Christ lived many years as a craftsman. Galilei reintroduced mathematics as a method of physics. From this moment on, not only geometry has been used as a method to describe space measurements, but also a time measurement was asked. Attempts in this direction were also undertaken by Galilei. To define time measurements means to introduce a new physical concept of time, different from that time which we encounter in our consciousness. To measure time requires reproducible processes. From where to take them? No one would take the weather for this purpose or the waves of an ocean. There is fortunately a process that seems to be very well reproduced in nature, the rotation of the Earth. But this is not suitable for the measurements of very short times. Thus, the task was not to look for reproducible processes, but to make them. The clockmaker, as a craftsman, was required. and the clockwork became the ideal of reproducible processes. We have today succeeded to construct clocks with very high precision, that is, with very high reproducibility. 10 to minus 14, 10 to minus 14 in the reproducibility. This new physical concept of time, defined by clocks, does not involve anything of what we as human beings call the moment now, the moment now. Such moments now do not occur in any physical theory, since no clock can tell me which of its processes happens now. The moment now enters physics only by our work as physicists, that is, as super craftsmen. What we have done, what we have stated as facts, was before now. What we will do and will state lies in the future after now. But there are no moments now in physical theories. But the physicists were interested in reproducible processes to construct not only clocks, but also machines for practical purposes. Who, for instance, would like to use a car, the behavior of which is not reproducible? The development of mechanics by Newton, Laplace, Hamilton, has created a theory which can describe very well such reproducible processes. It describes not only those which we have prepared, but also some found in nature, for instance, the planetary system. But what about processes such as the weather or the motion of water in a fountain? Nevertheless, Newton's theory is such a brilliant theory that the astronauts of today fly by Newton. The overwhelming success of Newton's theory has tempted the scientists to philosophical interpretations which later have been found false. These philosophical imaginations were confirmed by a new physical domain, the electromagnetic processes. This domain and its structure were detected by human actions called experiments. Such actions were indeed the actions of craftsmen called physicists. The philosophy launched by these theories claimed that all physical theories must have this form of a deterministic time evolution because of the law of causality. But if we disregard this philosophical superstructure, nothing else than a vicious circle remains. We try to prepare reproducible processes, and we make a theory for such processes. Then we say that we have detected by the theory that the processes are reproducible. This circle does not say that we have not detected a law of nature. We have indeed detected such a law of nature in the form that we, as craftsmen, can produce such reproducible processes in the domain of mechanics and electrodynamics. And today we use such processes in such abundance in our everyday life that we would not know how to live without them. The philosophy of the necessity of a deterministic dynamics was so generally accepted that today it seems to be a joke of the history of physics that one thought of the world as a big clock work or of human beings as a very complicated machines. Today we know very well how many and high efforts are necessary to make our technical products more and more reliable, and that nothing is perfectly certain. But one aspect of the picture of the world as a clockwork has been correct. Each of these dynamically deterministic theories leaves open the so-called initial values. That is, that part which can be prepared arbitrarily. Therefore, the question arose how the whole world was prepared. This question is still the same in modern cosmological models. We answer today by a Big Bang. But this too is only a relative answer, since it is an extrapolation into a singularity, and a mathematical singularity is no physical solution. In the past, one said, by God, prepared by God, or one tried to escape this problem of preparation of the total world. One tried to escape this problem by saying that the world exists for an infinite time. In this context, it must be emphasized that all claims are false which say that physics has proved the infinity of this or that. Don't believe such claims. Physics can never prove anything to be infinite, since physics is based on many but always finitely many statements and experiments. Physics can therefore only prove the finiteness of this or that, or can prove nothing. If we use the infinite sets in physical theories, mathematical infinite sets, these infinities are only clever extrapolations to hide our ignorance behind them. Therefore, any claim of an infinity of the world has nothing to do with physics. Such a claim can only be made in the context of a philosophy or religion. The invention of quantum mechanics as a description of atomic structures was such a shock for the philosophy of determinism that one felt it as a knockout of all hitherto existing physical theories, as a refutation of the law of causality, as a revolution in physics. But nothing of all this is true. Neither Newton's mechanics nor Maxwell's electrodynamics were abandoned. They are as good theories today as they were for our technical developments, even more important than before today. No revolution has taken place, only an evolution to new theories which describe new and more comprehensive possibilities for our physical craft. Only a wrong way of the physical development was cut off, a way which included philosophy as a method of physics against the installation by Galilei of physics as a craft. If one had held on to the principles set forth by Galilei, one would have avoided such a wrong way. You may say that it is much simpler to judge afterwards than in advance. But I shall now criticize in the same manner some aspects of present physics. An essential structure of modern physics is what one usually calls probability. And here again we find the most abstruse imaginations. The shock by quantum mechanics was so deep that one invented many fairy tales. If one takes a book which tries to describe microsystems as atoms in the form of popular science, one keeps wondering whether there are more fairy tales or more facts. Disappointed by the indeterminism of quantum mechanics, one tried to save what can be saved and invented the following fairy tale. It may be that the processes of microsystems are accidental and statistical, but for macrosystems consisting of many particles, the statistical deviations cancel because of the great number of particles. Thus, macrosystems get a deterministic dynamics. Sometimes one adds the following imagination. An electron as a single microsystem can freely decide what it will do, but many electrons behave deterministically. What about probability in physics? I said that is a fairy tale. What about probability in physics and especially in quantum mechanics? We have seen that the reproducibility of processes in the macroscopic world of craftsmen is not a general law of nature. It is only possible to select such special deterministic processes by special preparation procedures, or to find some in nature, as for instance the planetary system. We have also seen that for practical purposes, one makes great efforts to construct reproducible machines. Our working as physicists shows that it is not always possible to prepare macrosystems in such a way that the actions of these macrosystems, one each other, are reproducible. No efforts produce reproducible interactions of macrosystems. In such cases as the action of a piece of uranium on a counter. What can we do in these cases? If the single process cannot be made reproducible, we try to find such procedures which makes the frequencies of the various processes reproducible, repeating the experiments according to this procedure many times. Thus, we replace the demand for reproducible process by the demand for reproducible frequencies of the various processes. The demand of reproducible frequencies for machines is not new. The oldest procedure is that of throwing dice. Also very famous is that of a roulette. The craftsman must work very well to guarantee a good reproducibility of the equal frequencies for the various numbers of a roulette. This is necessary for the casino, excuse if I don't speak it very well. To make money, it is necessary. This is necessary, this very good work of the craftsman to make it for the casino to make money. But all these machines were fabricated for gambling. The new physical interest lies in such procedures where the frequencies cannot be made as one wants, but are determined by the procedures. In this sense, we detect structures of nature, for instance, in the case that a piece of uranium triggers a counter. The mathematical description of such reproducible frequencies is what in physics we call probability. In physics, these reproducible frequencies are always frequencies of macroscopic processes relative to macroscopic procedures. No probability for a single such process is defined. Thus, the microsystems are detected as action carriers from one macrosystem to another. We select for physical experiments only such interactions where the frequencies of the various actions are reproducible. To emphasize it again, the reproducibility is not coming by itself. We must make technical efforts to get the reproducibility. Quantum mechanics of microsystems, for instance of electrons and atoms, is nothing but a comprehensive theory of all these interactions of macrosystems by microsystems as action carriers. The structure of these actions by microsystems differs from that by macrosystems as action carriers with which we are familiar. Let us take two examples. A gun which acts by bullets on other systems, and an electron gun which acts by electrons on other systems. We know that with electrons we can make such reproducible frequencies for actions that these frequencies yield what are called interference rings. The same is not possible with bullets. The bullets can be described by the deterministic Newton's mechanics. The electrons cannot be described by Newton's mechanics, since this mechanics contradicts the possibility of interference patterns. The electrons can be described by the not deterministic quantum mechanics. Again, one wanted to efface the difference in principle by the following fairy tale. The difference between, in the example, bullets and electrons, the difference is caused, the fairy tale comes now, the difference is caused by the measuring possibilities. The trajectory of a bullet can be measured with such soft disturbances that the trajectory is practically not changed. The measuring of an electron cannot be made so soft that the disturbances can be neglected. Thus, for instance, I cannot know together position and velocity of the electron. Do not believe such fairy tales. In physics, it is not interesting what I know, but only what I do, respective can do, what I can do. Newton's mechanics for bullets can also be obtained if one allows only very hard measurements of the bullets. For instance, if I do only allowed to measure by the actions of the bullets on sandbags or metal plates, that are hard measurements. The difference between bullets and electrons is not due to the existence of soft or hard measurements. It is due to the fact that the electrons have much more manifold action possibilities, than bullets have. For instance, bullets cannot make interferences. This narrowing of the action possibilities as we pass from atoms to molecules, macromolecules, and finally to macroscopic systems is also the key to understand that the objective description of macrosystems is compatible with quantum mechanics. With this in view, we can return to the fairy tale of the deterministic dynamics of all macrosystems. This is wrong, since there are interacting macrosystems with an indeterministic dynamics. For instance, those macrosystems, the interaction of which was the base of the detection of the microsystems. If all macrosystems would have a deterministic dynamics, there would not exist microsystems at all. But can we say a little bit more about the dynamics of macrosystems? Yes, and I will try to make some remarks to this very complex problem. If we play tennis, this behavior of the tennis balls, is deterministic and can be described by Newton. More complicated is the dynamics of a gas, the aerodynamics. There are some regions where this dynamics is deterministic, but also other regions where it is indeterministic. There is a general law for all macrosystems. A deterministic equation of motion can only be a good description of macrosystems provided that the solutions are stable. A solution is stable if small variations of the initial values guarantee also small variation at any time. In the case of instability, the deterministic dynamics is false and must be replaced by at least a statistical dynamics. Thus, for a turbulent streaming of gases, the dynamics is indeterministic. The development of the weather is indeterministic. The famous law of increasing entropy is only valid for a deterministic and therefore stable dynamics. Therefore, this law is obviously very important for the construction of machines. On the other hand, it is not valid, for instance, for the indeterminate behavior of an aquarium with fish. Thus, we see that most of the systems we encounter in nature are not deterministic. Many of the artifacts we construct are deterministic, but only to the extent we succeed. You will perhaps wonder why we have never used the word chance or accident. That was not accidental, but intentional. In physics, it is not necessary to use, these words, chance or accident. These words are no concepts of science. Today, we are tempted to make the same mistake as our ancestors, who wanted to prove by philosophical methods that all dynamics must be deterministic. We are tempted to prove on the basis of philosophical concepts that for great numbers of repetitions, the frequencies are reproducible with high probability. Unfortunately, there are several philosophies which assert to give the right understanding of probabilities. It would require a voluminous book to describe all these philosophies. But let us only briefly mention two concepts of chance or accident. The one concept is an ontological interpretation. There is an ontological indeterminism in the sense that reality in individual cases can decide between several possibilities, that there is a certain propensity for the various decisions. The individual decisions is accidental in this interpretation, but because of the different propensities, a reproducible frequency for the various decisions results for high numbers of equal cases. If this ontological interpretation is used carefully, one cannot get a contradiction to the physical description. But this philosophical proof of reproducible frequencies is no more stringent than that of determinism by causality. I myself do not believe in ontological accidents, and a little later I shall say why. The second, I have to say, I do not believe. By physics, I can nothing prove. The second interpretation of probability is a subjective one. Probability is a weight for the occurring of the various possibilities. This weight depends on the knowledge I have before the occurrings. Such weights make only sense for events which will occur, and not for those of which I know that they have already occurred. The physical concept of probability can, on the contrary to the physical concept of probability, can, on the contrary, also be applied to facts that have already occurred. The subjective concept is not the physical one, and the physical concept cannot be based on the subjective one. The inverted relation is nevertheless correct. If I know the reproducible frequencies for the processes on a device, I can use this device as a gambling machine and can estimate my chances to win. The physicists are no gamblers. They measure only the reproducible frequencies. It is senseless to prove on a philosophical basis that in nature there are real accidents and that these must be controlled by propensities. In fact, physical theories not only describe possibilities constrained by reproducible frequencies, but also free possibilities. That is another point. Physical theories not only describe the possibilities constrained by reproducible frequencies, but also free possibilities. No ontological accident, with or without the propensity concept, can be based on science. I will give two arguments for this claim. The theory of the evolution of life on Earth is nothing but an application of physics to a given process in nature. You know that for this purpose, the concept of accident or chance is used on a large scale. It's right that this evolution is not a reproducible process. But what does the concept of accident mean in this context? It is not accidental that one uses the ontological concept of accident, since one wants to persuade the reader that science has found the conclusive explanation for the development of the world. The reader or hearer is all the more willing to accept the concept of accident as it is presented as a scientifically founded concept. But accident or chance is not such a scientific concept. If you replace the word accident or chance, for instance, by action of a ghost, all the scientific essence of the description of the evolution of life is not altered. I personally neither believe in ghosts nor in ontological accidents. I wanted only to demonstrate how easy it is unconsciously to add the philosophical imaginations to scientific explanations and to sell these imaginations as latest scientific findings. It is therefore the described explanation of the evolution false. If one takes the word accident or chance only as a synonym for the physical concept of a realization of a theoretic possibility, then the description proves that the evolution of life is not in contradiction to the known physical theories. But also the behavior of my brain is not in contradiction to physics. In this connection, one hears another fairy tale. A brain is nothing but a complicated physical process, more or less indeterministic. This fairy tale is again one of the famous vicious circles. The method of physics allows only such concepts which can be reduced to the actions and language of craftsmen. Physically real in this sense, physically real is only what can be detected by indications on devices. In contradiction to a vicious circle, this physical reality need not be the total reality. Why shall it be? And in the case of my brain, I know that it is not the total reality. There is no physical definition of a beautiful sound that I hear or a beautiful picture that I see. There may be correlations between these facts in my consciousness and the indications on devices influenced by my brain. But if physicists want to see by these indications whether I hear a beautiful sound, they must first know that the not physical concept of hearing a beautiful sound, and can then perhaps find a sort of translation of this concept in the structure of indications on special devices. They cannot first introduce a structure of indications and then define by this structure what is meant by hearing a beautiful sound. That this last way of reasoning is impossible follows from the fact that I can decide whether their definition is right or false on the basis of a knowledge I have before that definition. It wasn't no definition at all. Since my knowledge thus goes beyond the physical description of my brain, I sometimes can say more than physicists about the realization of a theoretical possibility. Inaccurately called accident. When the physicist measuring my brain says that a special process is an indeterminate realization of a possibility, I can say that I have, for instance, decided this realization. I have decided this realization. I know that this realization was not an ontological accident, but was a decision for which I am responsible. Thus, there is no contradiction between physics and freedom. In the contrary, without freedom, there is no physics. If one only had walked about nature as it is, and would have observed and observed and observed, no physics would ever have been developed. Not to see, but to do is essential for physics. The often invoked observer in physics is essentially active, mostly even creatively active. Observed are only indications on the devices, but this everyone can do, also one who knows nothing of physics. Today, such indications are recorded in memories of computers and then are at our disposal. A pure physics and an applied physics, it is a technology, cannot be separated. Today, physics is a widespread and connected network of theories and corresponding realities and possibilities. This physics comprises chemistry, biophysics, and very great parts of medicine. but it is impossible to realize all what is possible in this physical theories, according to these physical theories, but it is impossible to realize all what is possible, since there are not enough human beings and not enough time for such realizations. Thus, we must select what we realize, whether we like it or not. We are responsible for our selections. We can save life and destroy life, both with the help of physics. But we cannot construct peace as we can construct a bridge over a river. Peace is finally a gift and not a loot. I thank you.
I imagine that Professor Ludwig's paper will give rise to a multitude of interventions. Perhaps, if you'll excuse my selfishness, I may make the first one so as not to get left out for lack of time. Dr. Ludwig, of everything you've said, what surprised me most was the fairy tale, according to which the role of the observer in quantum mechanics has been reduced to the point that it loses the predominance it is usually given. The observer was nothing in classical physics and is practically everything in some versions of quantum physics. In your opinion, Professor Ludwig, what difference is there between the two now, from your point of view, if there really is a difference between the role of the quantum observer and that of the classical observer?
For me, there is no difference between the two observers. They observe the processes on macroscopic devices. And I said in my talk that this can do everyone, these observations in classical and quantum mechanical physics. But to conclude from these observed processes something, that is a task for the physicists. And in the case of quantum mechanics, we can conclude, in the case of microsystems, we have to use quantum mechanics to conclude on the microsystems.
I was confused by the last sentence. If I have understood correctly, you finished by saying that peace is a gift and not something that can be achieved. However, from your talk, one rather draws the conclusion that, in the last resort, we are indeed responsible of our choices. So, then is peace independent of our choices?
I don't know whether I have understood correctly the question, but you ask why peace is a gift. Why I said peace is a gift, and not that I want hint to the difference between the question how can we get peace and how can we make a bridge. The one is to build a bridge is possible by physics, but it is not possible by physics or something by science alone to make peace. We have to make other efforts.
But the efforts can be made by the man.
Peace can be made. Perhaps not. Perhaps not. But we can behave that we can get the gift of peace.
Sorry, Professor. I was wondering when hearing Professor Ludwig's talks whether he is a follower of Paul Lorenzen's theories. Namely, this idea that everything should be reduced to pragmatics. To replace knowledge by know-how seems to me a backward attitude, I would say, in a very, when I speak frankly. For me, for instance, if modern science started with Galileo Galilei, it is not because Galileo was interested in craftsmanship, it was because Galileo realized that at the beginning of the 17th century, two basic notions did appear in a fairly clear way in the mind of the people. First, the notation of real number as an infinite sequence of digits, which was found by Stevin and Viet. Second, the formation in the spirit of the people, or the mind of the people, of the notion of mathematical function. If you read Kepler's Astronomiae Pars Optica, you will find an approximation of the so-called Snell's law of the function of the refraction angle as a function of the incidence angle of the light through a plane diopter. So I believe that at the origin of modern science, two basic notions were really involved, namely the notion of real number and the mathematical notion of function, which in fact found its final expression only in Leibniz some 19 years later. Would discard this intellectual construction as being only ghost and having nothing to do with reality?
If I understand right your question, I would say, for instance, that the discussion of Leibniz, whether the differentiation had significance in reality, I would say that was senseless. The differentiation process, for instance, that is a mathematical to differentiate a function, is idealization, a very good and very practical idealization. But we hide, yes, excuse me. We hide behind such things as, for instance, the differentiation of functions that we do not know how is in reality the structure of space and time. We do not know it. And therefore we make the idealization, and that's a very good and very practical idealization, but has nothing to do, in my sense, with the reality. Differentiation has nothing to do with reality. The continuum has nothing to do with reality. That is a mathematical fiction.
I would perhaps agree with your statement that
you agree?
The structure of space-time is probably not the one we practically use in ordinary geometry and in ordinary classical calculus. But nevertheless, because of its usefulness, it has some kind of reality. It has to do something with reality. Even if it's not the ultimate form, and when you say the ultimate form, you seem to, so to speak, to rely on some sort of underlying ontology. And I understand from all what you said that you are strongly anti-metaphysics. Am I wrong? You are of a really positivistic type of mind. You do some sort of Machist philosophy, except the fact that Mach was more in favor of perception and you are more in favor of action, which is perhaps not a progress. And so I wonder whether your position is very coherent in that matter.
the use of these mathematics has a connection with reality. That I do not deny, that this mathematics had a connection with reality, also for me. But this connection is unprecise. Only when I add a finite unprecision, then this mathematics reflects with finite unprecision reality. That is also my meaning, my opinion.
I would say this connection is at least as precise as the one of the best physical laws, namely 10 minus 14ths, that was said earlier.
Excuse, I have no. Excuse, I did not understand at the moment. Can you repeat? Can you please repeat?
I said this connection of mathematics with reality is at least as good as the best approximation of physical laws, namely 10 power minus 14ths, as for instance the definition of time as a function of some spectral frequencies. And I think you may find even better approximation to some extent.
Yes, that is only good in the approximation we have today, and it can be that we have tomorrow better approximation, and it cannot be that we have finally the approximation cannot, in my opinion, be made precise, arbitrarily precise. That is in contradiction of my opinion of physics. There are no possibility to make the precision finer and finer, arbitrarily precise. Arbitrary is nothing in physics.
See, according to your methodology, you would say, I think you would agree, that physics might once prove that the universe is finite. But
that the universe is?
Finite.
Finite, yes.
But it may be infinite. But if it is infinite, physics cannot prove it.
Yes, that was what I wanted to say.
There is something similar to this. Physics can once prove that the universe is not Euclidean.
Is not?
Euclidean.
Yes.
But cannot prove that it is Euclidean.
Yes, that's...
Is there some connection between these two sentences, or there is no connection?
There are also models, infinite models, which are not Euclidean as models. But I only wanted to say, if you make a Euclidean model, and we cannot prove by physics, we can prove that the world is not Euclidean in the next region by experiments and so on. But it would be possible in thought that we would not in the position to prove that it is not Euclidean. But in the moment we have so good measurements, astronomical measurements, that we can say it is not Euclidean.
I have two very short conceptual questions. First on reproducibility. You said that all meaningfully used physical concepts depend on the concept of reproducibility. But I wonder, and the idea of reproducibility depends on the same events happening in time, I mean repeating in time. The same event repeats itself in time, and then you can see that it's reproducible. But this already presupposes a concept of time, of physical time. That is, in this sense, the concept of reproducibility depends on the concept of physical time, which would not itself be definable in terms of reproduction of processes. So I see there a sort of conceptual tension. That's the first question. And the second question is, if you define, say, electrons as the action carriers of interactions between macrosystems, in principle, one could ask why you need these things as electrons. Why do you don't just make a theory which describes in a mathematically correct way interaction between macrosystems without the need of introducing electrons as special carriers? And so if one reduces electrons as action carriers, perhaps they are just ontologically superfluous, just a way of speaking, as Mach would have said, by the way. So
that were two questions. The question of reproducibility is a very deep question. If I try to construct a clock, I cannot take the time before I construct the clock. And then I must give the experimentators some norms they had to fulfill. That is a very deep question. Perhaps we can discuss it later. It's not. I agree that the word reproducible in that moment is not very comprehending all these difficulties. But the second question is not so difficult to answer, because I can describe all this only by macroscopic descriptions. I have no need to introduce electrons, but it is very practical to introduce electrons. I have no, and by the theory, and you, I know what you will ask, but also in my interpretation, then the electrons are realities. They come out as realities from these interactions, as a structure of the interactions. But I can, at the first stage of affairs, describe only all experiments macroscopically without using the word electron. It is not only a practical introduction, it is also a insight that the electrons are real. They are detected as realities, but they are detected from the actions on devices, from the process on macroscopic devices. But that is what physicists do in experiments.
Only a minute, please. Sorry.
This is just another point of your philosophy which I didn't get. Namely, what is your position with respect to causality? Apparently, you are a positivist. You believe only on legality, and you give up causality as a kind of metaphysical residue. No? Or,
No, that's no physical concept, causality.
No, but when you say we have to do, as craftsmen who wants to do things, as soon as you use the verb to do, you are accepting some notion of general causality. Because causality is infused, so to speak, intricated into our language structure, and we have this grammatical category known as the verb, which describe causality. Which in some sense is motivated in order to describe causal effects. Now, would you deny any kind of reality to causal effects? And you would, so to speak, replace the general concept of causality by I would say a continuum of specific laws for each special case in which you use it.
I have not said that I have a physics without assumptions. I have the big assumptions that I know already, before I begin with physics, all what craftsmen do and speak. I make the assumption that we all know, that we understand what craftsmen do and what they speak if they make their doing. That is
But then the main point is to understand which is the ultimate references, the craftsman or the physicist, or the theoretical physicist. The craftsman or the theoretical physicist, you have to make a choice.
I have not understood at the moment.
Please understand?
You have to have a choice.
I am asking, who is the ultimate reference? The craftsman or the physicist?
The craftsman or
the physicist?
The Unterschied, there is no distinction between these craftsmen and physicists, but
No, please, por favor.
Well, I am worried about your remarks concerning laws of nature, because you state that we as craftsmen can produce such reproducible processes in the domain of mechanics and electrodynamics, and I suppose and so on, which I understand as meaning that for you, laws of nature is sort of artifact which is the produce of the human activity on the human brain, and that laws of nature do not pre-exist to physical investigations. And you base this argument on reproducibility and the fact that we as craftsmen manage to have instruments such that we can reproduce and so on. But I would say that as an astrophysicist, we are facing a situation where we never see twice the same thing. Reproducibility is something which do not exist in the sky, or I would say in many earthly situations, like you mentioned it, the weather. And nevertheless, it is not possible to try to understand what we see. It is not possible to reach an understanding of the observations with, in fact, a certain level of predictability if we do not fundamentally assume that there are laws of nature and that these laws of nature are operating in situ in the atmosphere of the stars, in the deep center of the stars, in galaxies, and so on.
Yes, it could make the impression, my words, that I have meant that the laws of nature have only this significance that we make something. That's not my. That was not my intention. But the other case that I say that laws of nature are something which I have found in nature, found as a law in nature. That is also not all of physics. That's not all. We have, if one makes a physical theory, if we develop a physical theory, we have to introduce many sort of laws. They have many, not the same significance, all these axioms in the mathematical sense. The one are laws of nature, as you say. There are laws which can be interpreted as being in nature. That's correct. That's also possible. But there are many other laws, in my sense, that I prescribe what is to do. I cannot make, in many cases, physics without describing what I have to do. And then you can say, you can describe many things, but I cannot do these things. The prescriptions are senseless because I cannot follow the description in physics. And in this sense, I say that if I can follow the prescriptions, then there are also laws of nature.
Can you give an example of a prescription which you cannot follow, because I have not understood your final conclusion?
Yeah, we do not make such, but it is possible to make a prescription that you. I have not at the moment of. For instance, it can be you make the prescription to divide a length in one half and to divide again in one half. And I make the prescription, make one half and one half and one half, and then it can be that it's impossible. At one stage, it is impossible to make, to divide the space in pieces. It is impossible. I make the prescription, but it's impossible. It can be. That I believe that it is so, that it is impossible, but at the moment I cannot say it. I cannot. I have no. That would be a prescription.
Yes, but I am not sure I have understood the example. Do you divide a piece of matter or do you divide space? Which is not the same problem.
For instance,
and if you divide space, you finally will reach some quantum impossibility. So yes. I really do not see if you.
Yeah, but better the example is better if you take a piece of metal.
Yes.
And then I make the prescription that's that's better. I make the prescription to divide it in two pieces, and then again to divide it, and the prescription is divided in more and more pieces, and then you cannot do this.
I don't think so. You just change tool at the proper time, and you reach smaller and smaller sizes until you just reach one layer of atoms, and you cannot go further.
Yes.
And then it's just because you do not have continuity. You reach the atomic level, which means that the prescription is not physically correct.
I cannot do this.
Yeah, I said the prescription is not physically correct because ultimately you reach the nature of atomic structure of matter.
But that is what I mean. That if as long as I can follow a prescription, this gives me something of the structure of the world that I can follow. In certain regions, I can follow the description to divide, but then I see that I cannot follow, and I have detected a new law. I don't know.
Well, let me first say that I do realize that you are not a philosopher of science, not a methodologist, but you are indeed a physicist. But hearing your presentation, well, it seemed to me that many of the things you were talking about were like a kind of methodology. In this sense, I will agree with Professor Doe when he began his question a bit before, speaking about methodology. In this sense, well, perhaps your ideas, as you presented them, do help to make sense, to understand, without paradoxes, present physics. Surely, they do help to you to understand physics in that way. It seems for the debate here that anyhow, that is open to criticism. But let me ask you my question. Do you think that your points of view will help physics in its future developments in his future development? If so, in which way will help physics, your methodology, I mean? And if I ask this, is because it seems to me that your, let's call it, methodology is playing too sure on physics and is a bit sterile about his possibilities in order to help physics.
Oh, I did not understand. Excuse me, the question. If you...
Would you say that you have a methodology? Do you have a methodology?
If I have a methodology...
Yeah, do you?
I have a methodology for physics.
Yeah, and this methodology, do you think will help physics as far as its future development is concerned?
Yes, but I have not the physics of the future. But I have only the methodological. I have only the methodology. Yeah. I have not the physics.
Yeah, that's evident, of course, but in which way will help your methodology future development in physics? Let me point you an example. When Karl Popper said that the methodology of science is such that one has to tend to look for, how it's called, refutable sentences, he's saying something very concrete. Maybe he's wrong. Do you have any kind of things, not certainly the same, but some points which one can identify, and when one could then speak about Professor Ludwig's methodology and understand what he's really saying for future development in physics?
I have a method how physics, how the fundamental structures of physics have to look like. But I have no method to develop physics, to find theories. That there is no method to to detect theories. That's my opinion. But but there is a method how have to look like theories, and how they are to be founded afterwards one has developed a theory by experiments and so on.
Yes, it's only one precision. I guess you said before that you believe in ontological laws, more or less, no?
Yeah.
But in your talk, you said that you don't believe in ontological accidents.
Yes.
At least it is in the same level in the same hierarchy of knowledge. You can. This is really how I am saying.
Yeah.
Yes.
Yes.
So everything is. This is a very.
It shows that that it is possible to define what I mean by physical real. I will distinguish by physical real, and therefore I am not in this sense a positivist, because I introduce the concept of physical real. That is possible. But it is clear that the step from physical real to ontological real is a little bit more. Yes, you are right. And I make also these steps, but not in the context of physics. I make afterwards.
So a second question then. Everything is law in nature then?
Everything?
Everything is law. Is a law in nature. Or is space, or if there is no accident and you believe in laws, so the space is full of laws, or is some hole for
I had given an example. You can say that if I make a decision, a free decision, physicists who have devices which are influenced by my brain, for instance, would say that is an accident. But I don't like the word. That is a possibility is realized. A theoretical possibility is realized. Then, in this case, I know I have decided, and therefore it is not an ontological, in this case, it is not an ontological accident. But that is no physical answer. That
well, you say that there is no place for chance or for accident, but that they are just realizations of theoretical possibilities. That, well, of course, if something is a theoretical impossibility, it cannot happen, neither by chance nor by law nor anything. But there are, perhaps at least prima facie, there is a difference between theoretical possibilities, which we have some means of predicting, and or retrodicting or whatever, and just theoretical possibilities about which we can no predict or retrodict or say anything. So I do not, well, I think in your quite fascinating reflections on all that, it was not very clear why to say that something which happens by chance is a theoretical possibility, eliminates the description of the realization of that theoretical possibility as a chance or an accident.
I do not, as a physicist, I do not know whether the realization is an ontological accident or not. As a physicist, I do not know what it is. It is a realization. But you are right that what is not allowed by a theory is not possible in this sense. That would be a contradiction to the theory. If it would be realized something what is not possible by, in the theory, it would be a contradiction. But there is an essential point of our theories, and not closed theory, not a physical, not closed theory, let open possibility which are not possible in nature. And that the intention to make our theories in such a way that they are not open, that they tell us what is possible in the sense that it may be in some circumstance to produce such things, for instance. There's a very essential question for physical theories. I mean, for instance, that my opinion is that quantum theory for microsystem is closed, or is closed for atoms and so on. But that quantum theory is not closed for bigger molecules, and essentially not closed for macrosystems. Quantum theories lets open too much possibilities for macrosystems which are not possible, and therefore we must make a better theory than quantum theory for macrosystems, which lets not open all what lets open quantum theory. And that is a sense that the cat is that or not that, and that the quantum theory cannot tell us that the cat is that or not that. The quantum theory cannot tell us this fact. But that is so in nature. There cannot be other possibilities.
Please, the last two questions. Because
this is not a question. This is a statement which I want to make after what has been said about methodology. In the office of Willy Fowler at Caltech, there was, and I think there still is, a poster which says that the terrible tragedy of science is the horrible murder of beautiful theories by ugly facts. And I think that this introduces very well my statement that a common methodology in physics and in science, generally speaking, is to look carefully at all possible disagreements between theory and facts. And this is the common methodology. And I believe that this has been the methodology and that this will be the methodology. And a very famous example, just one which came to my mind, was Max Planck. Because the black body radiation had a theory and it was completely in disagreement with the measurements, and from them stemmed the beautiful quantum theory of radiation.
That's also my opinion. That's not the words.
I have another question on a different thing. In your paper you said that the development of the weather is indeterministic.
Yes.
Now I would like you to explain that a little more, because I would have thought that if you know enough about the movement of the air, it would be deterministic. So perhaps there is something that might be worth exploring.
My opinion is on physical grounds that in the physical sense of physical theories, the weather is not deterministic. It is not correct to make a deterministic theory for the weather, because the deterministic theory has to be unstable. It is unstable, turbulences and so on. And in this moment, when we make a deterministic theory, there are instabilities, then this theory has to be replaced by a better one, by a more comprehensive, which makes, for instance, this tells us probabilities for the several possibilities, the better theory. The deterministic cannot tell us the real probabilities. That's my opinion on this case.
Then the discussion.
Also
Thank you.
Yeah,